Hey everyone, my name is Jeremy, and for the past month, I've been looking into how AI and robotics can be used to automate the sorting of different types of plastics and how, as a result of that, it can make plastic recycling actually feasible. One of the most important things to automated plastic sorting is the identification of the different types of plastic. Now, this is very important that any AI model can achieve human level accuracy in identifying the different types of plastic. This is a very difficult task to achieve, so I thought, why not give it a stab myself? Now, I wasn't able to find any reliable data sets online, which are specifically just regarding plastic. However, I was able to find data sets on more broader categories of trash. Which is contains soda cans, crushed soda cans, cardboard boxes, glass bottles, and plastic water bottles. So these are kind of the main uh, categories that I'm going to be creating a model which can classify the different types. So I'm going to highlight the process I took to build out this model as well as the result that came from it. Let's get started. All right, guys, so if you've seen any of my previous videos on reinforcement learning and Q learning, you know that I use Jupyter Notebook for my coding example. So that's what I'm using right now in order to train this model. Specifically, I'm going to be using PyTorch and Python. So let's get started. I'm going to just import all the classes that we need from PyTorch as well as other supplementary ones in order to get us started. All right, so these are our imports. We'll be using PyTorch, all the functional ones, as well as some math and random functions, and obviously NumPy and Matplot to visualize the data. Okay, so now that we've gotten all of our imports, we can start coding. The first thing I'm going to do is I'm just going to kind of build out our basic uh, model. I'm going to be using a convolutional neural network. So I'm just going to build this neural network out. So first thing we're going to do is create a network class. And I've very detailed explanations of what the different line of codes mean in my previous tutorial. So I'm going to be a uh, little more vague or a little more broad in my explanations today. So we're just going to make sure that this inherits all the properties of nn.module. So this is what these lines of code help with. I'm going to get that in. And now we can create the different layers of the neural network as attributes of this class. So we're going to do 2 convolutional layers, and then we're going to do 3 linear layers. So we're going to create the first convolutional layer, and this is nn.conv2d. And now the images that we're using are going to be RGB, so there's going to be 3 input channels. Channels equals 3, and we'll make out channels equals 6. Kernel size will equal 5. And I believe I do want to add padding equals same. I can't remember exactly if the standard is for padding to be same, but we might as well add it just in case. Next thing we'll do is add the second layer, and this is going to be much the same process. Channels here needs to match the out channels of the previous layer. Make out channels equal 12. Kernel size will be the same. And next, after our 2 convolutional layers, we'll create the linear layers. So we'll do self.fc for fully connected 1, and this will be nn.linear. And we have to make sure that the number of in features match the number of out features that are coming out of the convolutional layer. Now the convolutional layer is going to be flattened. So we need to think about 12 output channels, or 12, that's one dimension, and then the number of pixels in the other dimension. Now, I'll start with 12 times. So one dimension is the number of channels, the other dimension is the width of pixels, and the other dimension is the height of pixels. So in our case, we started with a 32 by 32 pixels. That's what this data set consists of, and I'll go more in depth into, I'll show you the data set later on. But in that case, this right here is going to keep 32 by 32 the same. That's what padding equals same does, and make sure that 32 by 32 is kept. However, I'm going to be using two max pooling layers. So in that case, it's going to decrease from 32 to 16 for the first max pool, which is going to be after the first convolutional layer. And then for the second max pooling, it's going to bring it from 16 down to 8. So I'm going to end up with an 8 by 8 image. So I want to have 12 channels by 8 pixels for height and 8 pixels for width. So this is the amount of features that is going to be going into the first layer. And of course, I need to write in features. Out features, we're going to have equal 120. And we're going to build our second layer. Similarly, this is going to be linear, and our in features have to match the out features of the previous layer. Make the out feature 60, and then we'll build our final layer, and we'll call this out for the output layer. 60 to match the previous layer. And then the reason we have 5 output features is because we have 5 classes that we're classifying, that we're categorizing. We have the soda cans, crushed soda cans, glass bottles, cardboard boxes, water bottles. So that makes 5 categories. Awesome. Now that we've built the layers as attributes, we can, sorry, my face was blocking, create the forward pass. So this is going to be what allows our data to pass through the layers, and we'll have T be the input data. So, sorry. Okay, so the first thing we do is pass it through our first convolutional layer. And actually, I'll do this in one operation. We also want to pass the ReLU operation to non-linearize, I believe is the correct term, this data, so it's not just a bunch of linear functions on top of each other. So we'll use ReLU for that, simplest and cleanest. And then we'll, like I said before, we're going to do a max pooling operation, and this is max pool 2D, inputting T, and then we're going to do kernel size equals 2, stride equals 2. So this is going to bring down our image from 32 by 32 pixels to 16 by 16 pixels. And we'll go to the next layer, and we'll say T equals self dot conv2 T, and of course we'll add the ReLU operation. Then we'll do another max pooling operation. We want to do the same kernel size and stride. This will bring down our image size from 16 by 16 pixels to 8 by 8 pixels. And then now we're entering the linear layer, so we want to flatten our data so it's just one dimension or 2 dimensions, the batch dimension, and then just all of the pixel values, or now all of the just values. So what we're going to do is we're going to use torch flatten, so we can flatten the dimensions, and we're going to set start dimension equal to 1 because the 0th dimension is our batch dimension, and we want to keep that one, but we want to flatten the everything after that, which would be the channels, the height, and the width. Now we can pass it through the first linear layer, and we'll the ReLU operation self.fc1 t, and then we can do that for the second layer. So new f.ReLU fc2 t, and then finally we have our output layer. So then we can just say output equals self.out for our output layer t, and finally we want to return output. All right, there we have it. That is our neural network class. So with the neural network created, we can move on to looking at our data. All right, so I'm here on Portland State University's website, and this is the recycling data set. So this, as we can see from the little bit of description here, it's a data set of 11,500 32 by 32 color images, and there's 5 classes, like I said. So there's going to be, it's equally distributed amongst all the classes, which is good. These are the classes that I mentioned before, and we're going to have 2,000 training images per class, which equals 10,000. So our training data set is 10,000 images large, and then 1,500 for the testing portion. So here they gave us the code to unpickle or to load the data set using NumPy. So here I can just copy and paste what they've given us here, and I can put it into our code. Of course, it's weird, so let me reformat this. Okay, so first thing we're going to do is open the training data set. So let's do that. Right, so I'm going to replace this file with the file path for my computer. I've already downloaded the data set, so I didn't show myself downloading it, but it's in my computer, so I can just set this to the file path, and then we'll run this. Oh, looks like I have a indentation. Forgot to indent all this. Okay, let's do it. And since I've already downloaded this data set and loaded it in previous files, it's not going to show any loading of the data because it's already happened. So we can copy and paste this, and all we need to do is change train to test, and then we can download our testing data set, but we're going to obviously make these different variables. We'll make it x1, y1. We'll run this. Awesome. Okay. So now that we have our data, I just want to show you guys what maybe some of it looks like. So I'm just going to pass. All right. Sorry about that, guys. And let me move my face back here. I had just copy and pasted this code, but I hadn't realized that I still had left the function. So it was like, what? You're not calling the function. Nothing's happening. But I can, since we're in Jupyter and we're using code blocks, we don't need to create this as a function. And I'm going to delete all of that, and we can delete it here as well. We don't even need import NumPy because we've already imported NumPy. We can just say with open, delete the return, and this should give us what we're looking for. Looks like I've misspelled the file directory. Let me see here. All right, guys, I found it. Recycled. This is not spelled right. Recycled. There we go. And I also realized I'm pretty silly. I just left this as file, but we need to also have the file path here as well. So let me put this in real quick. And there we go. We've been able to run that. Here we go. And same issue, recycled. Same issue here, recycled. Okay. And now we can have x1, and hopefully, here we go. So this is the pixel values that we get. And as you can see, they are scaled to 255, right? They're integer values, and they represent pixel values from 0 to 255. And in neural networks, we want to normalize our values between 0 and 1. So the first step that we're going to do is to normalize the data. So we're going to start with the training data, and we're going to say x equals x dot as type. And I want to make it, since it's an integer right now, I want to make it a float so it can have decimals. We'll do this for all of the values. We can do this for both the images. This is what x represents. Sorry, to be clear. X represents the images, Y represents the labels. So X is the images of the training, X1 is the images of the test data, then labels training, labels test. Now for the labels, we actually don't need it to be float 32. We can keep it as an integer because this just tells us which class it's in. For example, I can just print Y for you, and we can see that. What? All right, so I've fixed a few things. I had to rerun this, and also I had them all as X, but I had to switch X1 to X1, Y to be Y, and Y1 to equal Y1, so these match. And now when I print Y, these are the labels. And as you notice, the first three are 0 and the last three are 4. And this is because our data is all ordered. All of the images of the first class start, and then it's followed by all the images of the second class and the third class and the fourth class and the fifth class. So that's going to be something we need to take into account because we're going to need to shuffle our data when we actually start training the network. Okay, so the purpose of this was to normalize our images pixel values. So we're going to say X equals X divided by 255. We're going to say X1 equals X1 divided by 255. 255. Now, since we're using PyTorch, I want to translate this over to tensors in PyTorch. So we are going to do just that, and we're going to call train set the training images, and we can say torch dot from numpy input X, and we can say the test set equals torch dot from numpy. Okay. Next thing we want to do is make sure our labels are also tensors. So we'll do the same thing. We can say label train, and we'll just copy and paste this. Okay, here we go. And now that we've had that, I just want to see, we're gonna look at just, hey, we'll say train set dot shape. I just want to show you so we can confirm that it is indeed 10,000 images with 3 channels by 32 by 32 pixels. So let's see what we get. Here we do 10,000 images, 3 channels for RGB, 32 by 32 pixels. Okay, this is great. Now that we've made sure our data is normalized between 0 and 1, and we've transformed it into tensor data type, we are now going to get into loading the data and making sure it's ready to be passed into the neural network. Okay, so moving forward. Now we're going to load the data into batches, and we want to shuffle it. So we're going to use Torch's built-in data loader. So we can do, we'll say train set loader, and we can call Torch's data loader, which is torch.utils.data loader. And then we want to first start with what our data set is. So we'll say train set, and then we'll say shuffle, or so we'll say batch size. Set batch size equal to 64, and then we will do shuffle equals true. That way our data is shuffled. Now there's an issue with this, and the issue with this is that if we shuffle the train set and we have another tensor for our labels, then our labels and our images are not going to match up. So we needed to figure out some way to make sure the labels and the images are connected together, so when they're shuffled, they still match up. So I didn't know how to do this, so I had to look it up online, and I found this great code. So I stole it. So let me just grab all this code, and instead of saying that, we're going to paste this right here. And basically what this does is it does a for loop, and it goes through the length of the labels, right? Label train is all the labels for the training set, and for each label it shuffles both the image, the ith image, and the ith label. That way when it creates batches, they are connected. So this right here can be our train set loader, and then I'm going to copy and paste it and we can use it for our test set loader. We can just move this to test. Label dot. Here we go. Label in test. Okay, and let's run this. All right, so now let's just make sure that it works. We'll do a quick test, and we'll just run one iteration of this, and we'll do train set loader, I believe it's called. Yep. And then we'll break it up into image, label equals test, and let's just see if this works. Yes, it does. And one thing we can do is just print image.shape, and we can see we should get a batch of 64, but still have the 3 channels in the 32 by 32 pixels. And yes, we do. And if we do label.shape, we should have a batch of 64, but it's only one number for the label. And exactly. Okay. So next thing we want to do is create the instance of our network so we can start training. So we'll just say network equals network, make an object of this class, and then we will create our optimizer. We'll use the Atom optimizer, set it to the network parameters, and learning rate will equal 0.001. Okay. Now that we have this, let me just run this code. Oh, I'll run this one more time. Run this just in case. In feature. Look at that, we missed an S. Good thing to catch for us. So in features, there we go. Okay, now we can start creating our training loop. So we'll run different amounts of epochs, but we'll leave this as 1 for now, just because we will do a test epoch to see how it does. And we're going to check the accuracy at the end of each epoch. So we'll do total correct equals 0, and then denom will be 0, and this will be all the ones we got correct, and this will just be all of the images that we pass. So this will be the denominator to calculate the accuracy. All right, now we'll go through all of the batches. So we'll say for batch in train set loader, say we'll iterate through every batch like this. The next iter train set loader. So this makes sure every loop we move on to the new batch. And then we want to split it up between images and labels equals batch. Great. And then we can just run it through our network. So we'll say predictions equals, what is this? Network images, pass that through. And then we'll say loss equal, and we'll use cross entropy, and compare the prediction to the labels. Then we can print loss, optimizer, .0 grad, form backward propagation, then do a gradient descent. Awesome. Okay. Now we can see whether we got it correct. So we'll say total correct, and this will be like a counter. And prediction.argmax, and argmax returns the position of the highest value of prediction. So if prediction has 5 different values for the output of the neural network, and each value represents a different class, then this argmax will return what class the neural network thinks it is. And then we can say prediction.argmax in dimension, the first dimension is the actual predictions, the 0th dimension is the batch dimension, and we want to make sure this equals what the actual labels was. Okay. So dot sum, and then this will make sure, so for the entire batch, it will sum up all of the ones that, it'll add 1 every time that the prediction was equal to the label. And then dot item helps us return the actual integer value instead of a tensor. Without this, it would just return a tensor value, but we want to return the integer value within the tensor. Okay, and then we'll just say denom plus equals 64 because that's how big our training batch is, and then we can print total correct num times 100, and this will give us our accuracy over time. And then at the end of each epoch, we can also say print total correct divided by denom times 100. Okay, so let's just see what happens when we run this. Aha, predictions. I said it somewhere else. Where did I say it? Predictions. Total correct. Silly me. Here we go. And what do we have here? Okay, looks like, didn't see this, I have an extra parentheses, so it seems like I'm trying to call function, but it's a tensor, so all right, so now let's run. And here we go. We start out pretty low, and we're increasing in accuracy. And that is our first epoch. We have 42.426. So let's see what happens when we move this to 5 epochs. Let's see how high accuracy we can get. And I'll just let this run and I'll check back in with you guys afterwards. All right, so I ran this for 5 epochs, and then I ran it again for 7 epochs, and I was able to get 81.76% accuracy, which is not bad. It's a good place to start. But this is just on our training data, so it's not even on our test data. But obviously our next steps are going to be different tricks and hyperparameters to tune in order to improve our model. So in a future video, that is what we're going to do. We're going to be focusing on getting the accuracy from 81% to higher. But this is at least a good place to start to show that, hey, we can use AI to categorize different images of waste. And this is the tool that can be used and will be used and is being used to revolutionize the sorting of plastics at sorting facilities. So this is a great place to start, and I'll see you guys in a future video. Peace.